If you are comfortable, we can continue. For I have.
Yeah, yeah, yeah.
We are waiting for someone. Actually, I thought that it would be there for tomorrow only because same.
No, this was an additional session.
Okay.
So,
Okay.
it was scheduled only for 1 hour
Okay.
from
Okay. No problem.
6:30. So I was actually waiting for someone to join. So since now you have joined, I think we can get started.
Yeah. Okay. Yeah. One concept doubts I have, doubt I have, especially on the transformer element that we use, right?
Haha.
Uh, so that transformer modulus, how we take actually? Can you explain with any, I mean, any example? Because I was having a confusion how to calculate that modulus.
Okay.
When, for example, a particular problem, uh, maybe I'll share what the question I have.
Okay. Are you sharing your screen?
Yeah, just a moment. I'm just in the problem which is there in the assignment problem only. I'll share. Maybe. Are you able to see my screen?
Yes.
Yeah. Uh, this problem I'm talking about. In general,
Haha.
when we calculate the transformer modulus, how you take this ratio? Like,
Okay.
yeah,
Okay.
it is like the transformer modulus is based on the for example, here it is a kind of leverage problem.
Yes, yes.
So, so the ratio when you're putting this b by a ratio and the sign, so how it would be taken? We can explain that. Would be useful. Yeah.
Okay. So just a minute. So I am just uh, so this was, I think, the concept from the bond graph modeling. Uh,
Yes, yes, from that chapter only, basically, from the bond graph
the
modeling
basic
only.
elements of
Right, right.
the bond.
Bond graph.
Yeah, yeah.
Right.
So here, like, there are, like, generally, like, we have those concepts of flow and effort,
Ah,
and so here it is like uh, so the torque torque about that fulcrum. So if this thing is to be, I think, balanced, then the torque about that fulcrum point should be uh, balanced. So by that we get the uh, the torque balance will govern the uh,
okay. If I take the moment about this fulcrum point,
yes,
so it would be like, for example, if I'm taking the effort thing, that is like force into the this distance,
yes,
and it would be equal to, I think, this will
yes,
create a
yes,
moment of
yeah, F1
uh,
into A, yeah,
yeah, F1 into A is equal to F2 into B.
yes, yes,
So uh, so the minus sign it is coming, and the ratio also how we are taking, like this the output ratio to input, or how it would be like here. So F1 into So this transformer modulus, if you multiply the input effort with the this transformer modulus, we should get the output effort. It is like that.
Here I think what happen it's like happening is that the the torque of the like both the forces,
Uh-huh.
I mean the directions of velocities
Hmm.
is same.
Right, right,
Both the forces are trying to pull the thing up. Uh, so the torques are like opposite in sense, right?
right, right,
So then they are not trying to turn the kind of like the like that beam. So physically,
right.
what we can say that it's not like trying to turn the beam about that fulcrum point, but it's like trying to do opposite to like thing, kind of bend the beam about that fulcrum point. So so that uh, that part should I think leads to that negative sign. Uh,
In the sense, since they are in the opposite direction, the torques are
ha,
of opposite direction. It is like that.
yeah. So just let me show you the
Okay,
corresponding slide. So I'll just share my screen now. Uh,
okay, okay, sir. Okay.
so so let me just share the like direct example that is given in the slides itself. I think that should answer our
Okay,
question.
okay.
So can you just
Yeah, I'll stop sharing.
uh,
Yeah.
yeah. So I have just opened up the slide corresponding to that lecture. So are you able to see my screen?
Yes, sir. Yeah, I will see.
So now here we like if you look at the third example here for the transformer element. So we have that same beam kind of example where now this x1 dot and x2 dot now are in. So x1 dot is like down and then x2 dot is above.
Right,
So here the transfer function transformer modulus is positive like b by a, right?
right,
Uh,
right, right,
but in the problem that we have been given, so the direction of x1 dot is opposite.
right, right.
So I think that is the cause of the negative sign
Okay.
because the sense of the moments are like opposite.
Oh, okay, okay,
Because
okay.
and here
Understood.
it's like trying to turn the uh,
Yeah,
beam about
full
that
beam.
so it's in that sense like the transformer modulus is by a.
Okay.
So does that answer your question?
Yeah, yeah, that is now got it. But when we are taking this modulus, why it should be b by a? Is there anything like it should why it can't be a by b?
Uh, so if we so I think that is I think dependent on the direction of causality that we assign.
Hmm.
Uh, like the here we assign the causality in a particular direction. So then uh, so like
Oh,
if we can actually also write the same thing by writing like the bond graph, drawing the same bond graph in the opposite like thing like from we can draw like bond from that x2 dot f2 then tf and then the f1 and x1 dots to the right side. So that will
oh,
reverse the direction of the causality. So I think this is some kind of standard uh, like so depending on the direction of the causality. So the I think the ratio is governed by that.
okay, okay. Yeah, got it, sir. Yeah,
Yeah.
yeah. Thank you.
Hello, welcome, Mr. Satish. Acha, he left. Someone had joined. Yeah, okay. Anyway, my
Okay.
my original plan for this session was to just give you a brief overview of what all concepts were covered in each week, uh, and then give a small demo on that same example that we had discussed last week on Simulink. So how we can
Okay.
solve the same example using just MATLAB script. So,
Okay. Okay.
so did you have any other question right now?
Right now, I don't have. That is the main
Okay,
thing. I was thinking.
fine. So
Are you
then,
going to conduct any session for tomorrow, or this is the final session that you want to
no,
conclude?
tomorrow there will be another session.
Okay. Okay. Then fine. I will
Yeah.
just go through the other concepts. If I get any
Yes,
questions,
yes.
then I make. Okay.
Yeah. So
Sure.
tomorrow's session is about the week 8 content, and this was like just a general session overview session kind of a thing. So it was actually supposed to be ideally it was supposed to be done after the week 8 session, but since I was not well, so I am conducting it before the uh, week 8 session.
Okay.
Okay. So I'll just give a quick overview of what all topics we had covered in every week, and then we can then look at the MATLAB demo example. So the content for the first week was basically provided an introduction to modeling and simulation, where the concepts of modeling and the different kinds of models were discussed, like physical models, mathematical models, etc. Then the concept of simulation, basically how like solving set of differential equations uh, with respect to time, and then using MATLAB as a simulation tool for solving uh, such problems using different simulation methods. So MATLAB can be a powerful simulation tool. So that was discussed. Then the content for second week was dealing with mainly bond graphs. So how can we use this graphical technique uh, for modeling systems? So this is like a graphical representation. So and there are basically certain set of standard elements by which we can represent this like multi-domain systems by using the same set of tools. So that's the interesting thing about this graphical technique. Then the concept of causality was discussed, and then how can we generate the system equations by looking at the bond graphs, and some methods of drawing bond graph models for electrical and mechanical systems were discussed. Then in week 3, we basically discussed the uh, just a moment. Sorry, I'm just getting a call.
Yeah, okay. Okay, sir.
Hello. हाँ. हेलो कौन बोल रहा है? सॉरी. नाही नाही रामला म्हणून सांग. देखील चालू आहे. Sorry for the disturbance. Uh, yes. In week 3 we basically discussed like the basic system models for mechanical, electrical, hydraulic, pneumatic, and thermal systems. So we looked at some examples for how the system models look like for basic mechanical, electrical, hydraulic, and pneumatic and thermal systems. what are the like typical differential equations and how do we represent them and using a bond graphs. Then the content for week 4 was dealing with the concept of linearity and non-linearity in systems, and then the uh, system models for like different types of systems like combined rotary and translatory systems, electromechanical and hydromechanical systems, and for robots where we have like the combination of all the above mentioned uh, systems. Then the content for week 5 was basically dealing with the dynamic response for first order and second order systems, and then how do we define some performance measures by which we can uh, quantify the performance of second order systems. So these performance measures were basically like uh, rise time, settling time, then the overshoot, which basically measures how fast the system responds, and how stable, like the stability of the system. So, so all these performance measures uh, are the measures of these kind of criteria. Then the concept of system transfer function and how to derive the transfer function, like the S domain transfer function, using the concept of Laplace transform. So the Laplace transform is applicable to linear time invariant systems only, um, with zero initial conditions. So that was discussed, and the typical types of transfer functions for second order systems were discussed, where uh, the the usual concept of the how the like the with the change of parameters the system behavior changes. So the system can be uh, underdamped, critically damped, or overdamped. So those parts were discussed. Then in the sixth week we discussed uh, the technique of block diagrams. So how do we represent graphically the transfer function uh, using block diagrams, and then the technique of signal flow graphs was also covered. The Then the concept of state variable formulation was also discussed, where we basically uh, split the, like let us say if the system is of nth order, the governing differential equations, let us say if they are of some nth order, so then we split the nth order differential equation into a system of n first order differential equations, and then we represent this in the form of a state space uh, equation. So that is the state variable formulation, so that we discussed. And then the frequency response, basically the response of the system to a sinusoidal load. So how do we derive that, uh, and so this is especially important in like different kinds of systems, like how the behavior of the system changes with respect to frequency. So we may be interested in the behavior of the system over a certain frequency range, and uh, whether we want to avoid some ill effects like resonance or something like which uh, might arise in a certain frequency range. So then we can design the system, or basically design controllers so as to create the desired behavior. Then the concept of Bode plot, which is uh, a slightly different representation of the frequency response itself. So it so Bode plot has two parts. Basically, it has the magnitude plot and the phase plot. So the magnitude is represented as a gain in decibels, and when we draw that uh, plot on a log scales generally, so that we call it as the Bode magnitude plot. And similarly, when we plot the phase with respect to frequency, so that is the Bode phase plot. Then in the previous week, which was the seventh week, we discussed how we can use Simulink as a simulation tool for different kinds of problems. So the lectures deal talked about some of these examples like simple pendulum, planar mechanisms, wheeled mobile robots, and so wheeled mobile robots, in the sense it was basically talking about the theory of like the holonomic and non-holonomic constraints, and then the techniques of validation and verification of models. So that was discussed uh, in our previous problem solving session. We had discussed the examples of simple pendulum and a simple spring mass damper system. So how we can use Simulink for modeling the simple pendulum. So in case of the simple pendulum, we also incorporated the viscous drag and Coulomb friction. And in case of the spring mass damper system, we discussed how we can use Simulink based models as well as use uh, Simscape multibody uh, toolbox for modeling that system, where we get the same results even with the two different techniques. So the contents for next week, which is eighth week, or we are in the current eighth week itself. So the uh, concepts for this week are basically parameter estimation, system identification, and optimization. So where we so in parameter estimation, meaning that when we have a certain model and the parameters are unknown, so then we can use certain parameter estimation techniques. So by applying linear regression and then using least squares method, so how we can use that method to uh, derive the unknown parameters. Then the concept of system identification is also discussed, where how we can fit a model onto a certain experimental data. So if we have a experimental data set where we know what are the inputs and what are the outputs, then we can use system identification techniques to fit a model onto the data basically, or derive the model that is represents the relation between the input and output. And then the concept of optimization is discussed, like so the basic theory of optimization and then its application to different engineering problems has been covered. So we'll be talking about that in tomorrow's session. So that was a brief overview of the overall content, course content that has been covered. So any questions, comments?
Yeah, no, sir. You can go ahead.
Okay,
Fine.
fine. So then I wanted to discuss about the basically the same example of a simple pendulum. So we had derived the differential equation, so which is theta double dot is minus g by L sine theta. And now if we want to use MATLAB, uh, mm, like instead of Simulink, if we just use MATLAB scripts to solve this differential equation numerically. So how can we do that? So that I just wanted to show. Uh, so so if we want to represent this differential equation in a state space form, so then we define a variable s as is so theta dot is s. So then theta double dot becomes s dot. So then the second differential equation becomes s dot is equal to minus g by l sine theta. So by introducing this intermediate variable s, we have split the second order differential equation into a system of two first order um, differential equations. So now then we can use the uh, numerical solvers in MATLAB like ODE45. So where we need to give the equations of the uh, like we need to express the equation in a state space form. So we need to give the differential equations in that form for the solver. So let me just open MATLAB. So are you able to see my MATLAB screen?
Yes, sir.
Yeah, okay, fine. So I'll be just going through the code which I have written already. So here this in this section we just clear the workspace and close all any open figures if there are. This is like this section is just to set, these are basically settings for the figures that are generated. So like line width and but they are not important. So they are just needed to get some desired graphics inputs like uh, then the input parameters for the simple pendulum are basically just the acceleration due to gravity and the length of the pendulum. So we assume the length of the pendulum as 1 meter. And the next part is the initial condition. So which is basically the initial angle of the pendulum and the initial angular velocity. So let us say we assume that the we displace the pendulum by a certain angle and then uh, release it. So the initial angular velocity is 0 and the initial angular position is, let us say, minus 60 degree. So with respect to the vertical, and so we define a vector uh, t span which gives the time span over which we want the solution, and then we define a vector y naught which is basically the set of the initial conditions theta naught and omega naught. So that is one of the inputs to the solver. And then for the ODE 445 solver, we need to provide basically the the syntax. It's in this form. So we need to define a function which gives the system differential equations, and the differential equation should be in a form which is basically the state space. So if you like go through the documentation for OD45, so there we can get a clear idea. So So in the documentation, it is given that it integrates the differential equations in the form y dash is equal to f of t comma y. So it's basically in the it should be in the state space kind of form. So then we define this function. So here we are creating a function handle. So function handle is basically like a kind of a an object which gives points towards the function. So we define a function named simple pendulum ODE, which takes the time, the current state x, and the parameters like g and l. So those can we have the option to define those parameters either within the function itself, or we can pass them as parameters to the function separately. So here we write this function in this way. So here if x is the set of state variables or state vector, so then the function should return x dot, the vector containing the derivative of the state variable. So basically, if in this case of the simple pendulum, it's basically the um, state vector is basically theta and s vector. So here we basically use the so the first differential equation is basically theta dot is equal to s, and s dot is minus g by l sine theta. So since theta dot is equal to s, so our state vector has two uh, values. So basically theta is which is x of 1, and second value is basically theta dot. So that's why we write so x dot. So the first row is x2, and minus, and the second row is basically minus g by l sine theta, which is x of 1. So so this is how we express the um, x dot here as a function of the state variables. And now if we had defined the parameters of g and l inside this function itself, we can do that. But let us say if we want to retain the same, the function and everything, but change the length of the pendulum and see what happens. So then every time we want to change the length of the pendulum, we have to again go inside this function and change the length and etc. So in order to avoid that, so we can pass them as parameters to this function additionally. So then we can have a top level script where we define the parameters, and then if we want to change the length of the pendulum, we can just change it here. It will automatically reflect in the subsequent uh, function also. Then so while creating this function handle, so we specify that we are solving for time and this state vector x, so that the solver knows that the next four arguments which are being passed are additional parameters. So this was about uh, how about the how do we write the code with respect to for like the inputs for this OD45 function. So are you able to follow up to this point?
Yeah.
Okay. So then another thing which I have done here is that we have the analytical solution for small angle approximation. So where we assume that sine theta is nearly equal to theta. So then we get the solution to be sinusoidal. So then because the differential equation becomes theta double dot is equal to minus g by L theta. So then the natural frequency is root g by L. So then it becomes the analytical solution becomes like theta naught cos omega n t, and then the angular velocity will become minus omega n theta naught sine omega t. So we also derive the analytical solution for the same set of initial conditions, and then we compare the plots of the uh, numerical and analytical solution, and then we can see how the behavior of the solution changes as we change the initial conditions. And so let us say if we set the initial angle of the pendulum as just 10 degrees, so we just displace the pendulum by 10 degrees and release it, then as expected our numerical and analytical solutions match very closely. So here we see the plot of the angle and the angular velocity with respect to time. So this is a purely undamped uh, oscillation case. So then that's why we get a more or less sinusoidal behavior. But now if we start increasing the angle, so now let us say if we make it 20 degrees, we start seeing some deviation of the analytical solution from the numerical solution. And as we go on further increasing the initial angle, so we then see that the deviation of the numerical solution is significantly greater from the analytical solution. So we see that the so the numerical solution is more accurate here than the analytical one, because it does not assume any small angle approximation. Uh, so this shows us like the utility of the numerical methods of solving differential equations. So in some cases we do not have the analytical solution itself, but in the cases where we have, we can compare those solutions like this way. Now if we even increase the angle further, then we see that the solutions are nowhere close. uh, so they are close for a very small time interval, and then they begin deviating quite a bit, and then after some time again they are uh, somewhat close. So so that is probably because the the actual solution is kind of non sinusoidal, but with so after a few cycles it again merges with the analytical solution, which assumes the same time period. So like that. So this was the demo which I wanted to show for a simple pendulum using MATLAB. So any questions or comments?
No, sir, it's fine. I'm able to understand it. Yeah.
Okay.
Basically, in the analytical solution, when you are increasing the theta naught, because of the small angle assumption, we are
Yes.
getting the discrepancy between the analytical and the numerical approach.
Yes. Yes. Yes.
Okay, okay, clear. Thank you.
Yeah. And then similarly now if we make our problem slightly more complicated, like if we have a simple pendulum but it is like, let us say if it is hitting a wall at a certain angle, then how do we solve those kind of problems? So any idea how do we solve that kind of a problem in MATLAB?
There would be a kind of forcing function because of that wall obstructing the pendulum, and the pendulum will have a
So if suppose like if we
kind of
uh
impulse input.
yeah, if we give enough energy to the pendulum uh, initially so that it definitely hits the wall, let us say, uh, and then so at
Okay.
so then there will be an impact. So when like if you want to visualize that, so like it will go and hit the wall, and depending on the nature of the collision, so if the collision is elastic, then there will be no loss of energy, so it will just bounce back with the same kinetic energy. But if the collision is inelastic, then uh, there will be some loss of energy. So then the velocity with which it will bounce back from the wall, so that we can find out using the coefficient of restitution. So we can define a coefficient of restitution which will give us the the reflected velocity after each collision, after each impact, and then we can keep a track of that, and then it will do the next uh, cycle. So when it bounces back from the wall, then with that kinetic energy it will reach some maximum angle. So let us say if we release it with a 60-degree angle, then if it hits a wall which is at, let us say, 40 degrees, so let us say if there is no damping present in the system, so if we release it by 60 degrees, then it's expected to go up to 60 degrees on the right hand side, and then if there is no wall present. But now if there is a wall present at, let us say, 40 degrees, then it will have some kinetic energy left, so then it will bounce back with certain kinetic energy. If let us say the coefficient of restitution is let us say zero point 0.8 or something, so then it loses, let us say, 20% of the momentum. So then the velocity with which it will be reflected back will be 80% of the earlier velocity, and then with that initial velocity it will again go to like move to the left side, and then it will again reach a certain maximum angle, but that angle will be less than 60 degrees. So with each uh, subsequent collisions, it will lose a certain amount of energy, and then finally it will have barely enough energy so that it will just reach the wall. So then after that it will keep oscillating. uh, so that is the concept. So how do we incorporate that in MATLAB? So any idea?
Uh, no idea.
Okay.
Yeah, actually, it will reduce, as I mentioned, that it will reduce the velocity. So, you have to calculate the other velocity, I mean, the other
Yeah.
position. Okay.
So first
Okay.
let me just first run and show you a sample output. Yeah. See, so in this case we assume that the pendulum was released with angle of minus 150 degree, and then there is a wall at 40 degrees. So here it the angle reaches to up to 40 degrees, and then it reverses. So it's bouncing back, right? So then, so in the angular velocity we can see that change. So here the angular velocity was something, and then it suddenly reverses its direction. So that shows that impact has happened here. Excuse me. And with each subsequent, so now here it bounces back again from here, and then it again reaches a maximum angle now of about 105.8 degrees, so which is less than the initial angle. So likewise in then again with that maximum angle it will again reach that wall and hit it, and then again it will lose some energy in that collision. So it will reach smaller and smaller angles with every, so here the sign is negative because we are looking at angles which are clockwise, in a clockwise sense, so that's why negative. So with respect to the vertical, so but magnitude wise we are basically will be reaching smaller and smaller uh, and maximum angles, and then so so here we can see there are sharp changes in the angle, and then after a certain point we see that the uh, there is hardly any change in the angle of the pendulum, because it barely just manages to graze the surface of the wall, and then onwards it will not lose any energy. So then, so after, let us say, around 20 seconds or so, it will stop hitting the wall. It will just go and touch the wall, and so then onwards it will continue oscillating at plus minus 40 degree kind of thing. So qualitatively this is how it would look like. Now how do we incorporate this in MATLAB? Any idea?
Uh, with the function we velocity we will give it in the form of some exponential function or something like that. Reduction
Now,
reduce.
now in the solver, now to actually achieve this, so in the solver we need to basically detect each impact event. Uh,
Oh, okay.
so for that, so like what we have to do is, so we need to tell the solver that we have reached the wall, so now stop solving, and then uh, record the solution up to that uh, interval, like time interval. Then uh, the event of bouncing back, so we incorporate the coefficient of restitution, and then it's basically starting a new oscillation with a new set of initial conditions. So just after impact, we are starting with a set of new initial conditions, like let us say with a new angle, initial angle, and new initial velocity. And then we again solve the same differential equation but with an updated set of initial conditions. And then we continue solving the differential equation till the next collision event occurs. So we can keep track of the angle that the pendulum has reached, and that the instant at which the pendulum will reach that angle, uh, we will keep track of that, and then we stop the solver at that time instant and record the solution from the initial conditions at which we had started up to the next collision event. And likewise we construct piecewise solutions and then join them together to construct the overall entire solutions over the entire time span. So qualitatively, this is how I think we can, like I could explain the uh, process. So in MATLAB, in the OD45 solver, so we have, so in the syntax for the OD45 solver, we have like the default syntax in which we just give the function handle, the time span, and the initial conditions. But then we have the functionality to pass additional options to the solver. So you can go through the documentations to get some more idea. So then we can go to this link of summary of ODE options. So here we can use this to tweak the solver, like the different, we can control the solver behavior, like we can change the tolerances uh, of numerical integration. So there are like lots of options, and there are different solvers that MATLAB uses. So in that, so there is a topic known as ODE event location. So you can go through that. So we are using this events functionality in this example, is that we, in this options part, so we give an event function in that, include that event function in this option structure, and then so we first create an option structure and then pass this event function to that option structure, and then give it to the solver. So this solver will use this event function to detect the event. So in our case, the event is what? the angle theta of the pendulum has reached, let us say, 40 degree, which is the wall location. And then we need to, so this is the syntax for the function. So in this is terminal is equal to 1. So this we need to set this option as 1. uh, so when if we want to terminate the execution of the solver when this event occurs, so we are using this thing, this concept. So I think it's already past 7:30 now. So maybe I think we can continue with this example in tomorrow's session. So we can close the session for today. So were you able to follow whatever we discussed till now?
Yes, sir. Yeah, we can continue.
Yeah, sure. So then, yeah, so we can discuss this example further in detail in tomorrow's session.
Okay.
Okay.
Thank you.
So in the meanwhile, you can go through the documentation.